Today we'll be looking at our third set of notes from Chapter 8, dealing with how do you handle polyatomic ions and draw them, what is resonance and how do you represent it, and how do we handle non-octet substances. Now, I'd mentioned polyatomic ions are a little bit different, so let's try at least one here. In polyatomic ions, we do have a covalently bonded group of substance, so N minus A equals S does still apply, but it's gained or lost electrons, so we have to account for that in our N minus A equals S. What you do is you account for the electrons gained or lost in the A value. And the easy way to think of this is find A just like we did before and then subtract whatever the charge was. And that will appropriately fix A because a negative charge means we have extra electrons. It gained electrons. So my A should be going up. Well, 6 minus my charge, if the charge is negative, is going to make it go up. Now, if we're going to draw NO2 minus, first we follow the process, NaS. So N. I have 3 non-hydrogens. That's a total of 24. A. Nitrogen is in the 5th column, oxygen is the 6th, so each nitrogen needs 5, each oxygen needs 6, that's 17. That looks goofy. 24 minus 17 is 7, that's 3.5 bonds. That doesn't make any sense. That's because I forgot to account for my charge. If I subtract my charge, which in this case is a -1, 17 minus -1 is 18. So I really have 18 available because of that negative charge. So I'm really sharing 6 electrons, which means 3 bonds. So when I go to draw this thing, I'm going to have my nitrogen, and then I just space out my oxygen. I first connect with single bonds, but I need 3. So that means one of these 2 oxygens, and they're the same. So I'm going to stick it over there. Has to have a double bond. Now I add my dots. Nitrogen has 3 bonds, which is 6, so I need a pair there. The double bonded oxygen has 4, so I only need 2 pairs to get my 8. And my single bonded oxygen needed 6. So I've got to put 3 pairs. Now, since it's a polyatomic ion, last thing we got to remember, brackets and charge. Now, this brings up a unique point here. I could have put that double bond in either spot between my 2 nitrogens. And technically, it turns out in the real world, it's partially in both. And that's an idea called resonance. When one Lewis structure does not correctly represent the molecule, you have what's called resonance. It's always going to happen when we have an equal choice about where to put our multiple bond. We had 2 equal O's here. We could have put it to either one. It looks like it's partway in both. So those electrons in that double bond, that second bond, are actually equally shared between the 2 situations. So it's like they spend half their time at one single bond and half the time at the other. So they're not localized between the atom, they're actually delocalized. They move throughout that whole bond region. So one picture doesn't really adequately show how it will exist, so we draw both and connect them with a double arrow. And remember, what's really happening is all those spots are sharing that bond, so they all partially get it. So you draw all of them and connect them with double arrows to show that it's a resonant situation, that double bond is shared throughout all the bonds. So in this case, it's kind of like 1.5 bonds on each side. Now, the last thing you got to watch out for with drawing is when you have non-octets. This seems like it makes it harder, but actually, it's going to actually make it quicker. N minus A equals S only works for octets. So if we don't follow the octet rule, we have a non-octet center atom, we can't use the N minus A equals S. It won't give us any valid information. So the first thing you should do before you do N minus A equals S is quickly decide if it is a non-octet, and then go right to the number of bonds and draw it. We get to skip Na and S at that point. So what do we look for? Well, first, less than an octet. You've already seen hydrogen, so you've seen a substance that does this. But hydrogen you're used to, and based on our electron configurations, it makes sense why hydrogen only needs 1 more and it's done. Some of the others are kind of a hidden situation. Boron and beryllium are 2 things that do this. So watch the top of the second column and the top of the third. Beryllium and boron. Beryllium, because of its small size, can actually be stable with only 4 electrons, which would be 2 bonds. So you literally would draw Be with 2 single bonds and don't put any dots around it. So if I see I've got Be, I cross out my NaS, I go right to the bonds and I write 2. And then when I draw it, I don't put any dots around it. Boron does the same thing, but now it's going to form 3. It's really for the same reason, very small atom, so it can be stable with only 6 shared electrons, which would be 3 bonds. So really, you're going to draw a boron, draw 3 bonds off of it, and then no dots. So that's really the key. If you see you've got Be or B, 2 bonds and 3 bonds, and you're done. The only other situation to watch out for is actually one that's easier, because when you go to do N minus A equals S, everything will be goofy. Expanded octets, things that can be stable with more than 4. And there's not a ton of things that do this, but you will see it from time to time. So the central atom actually needs more than 4 bonds because there's more than 4 things stuck to it. PCl5, SF6, you obviously have more than 4. So you skip NAS, go right to the number of bonds. PCl has to have 5, SF6 has to have 6. So you just draw them. So that's what SF6 would look like. Yes, that sulfur has more than 8, but that's the point. It's an expanded octet. But notice our fluorines are on the outside. Those still all follow the octet rule. They each need 6 dots to get their 8. So when you go to do this, you quickly think, is it non-octet? So here's a few examples. First one, I see BE. Okay, BE, second column, only forms 2 bonds. So I'm just going to skip all those and go right to the number of bonds 2. And then I just draw it. BE with 2 single bonds coming off it. Notice I didn't put any dots on the BE and it's done. But I put my 6 dots around the CL. PCl5, expanded octet. So I skip those. It automatically has to have 5. So P in the middle with 5 single bonds. Notice my outside still have to follow the octet though. And the last one, boron, that's got 3. So I go right to 3. And when I draw it, same thing. 3 single bonds, no dots. Notice this time it was with hydrogen, so I didn't need to put any other dots in there as well. And that is what I wanted to teach you about drawing molecules. I hope this helped if you were confused.